Now you may remember that there is a number of scaling relations between properties of galaxies and their central massive black holes, whether or not they're active. Today they're mostly inactive. And these are pretty good correlations. The properties of galaxies are measured of scales of kiloparsecs or tens of kiloparsecs. Supermassive black holes are on scales of microparsecs. And so it's really puzzling. How can there be such great correlations over such disparate spatial scales? So this already suggests there has to be some connection, interplay between galaxy formation and evolution and formation and evolution of their supermassive black holes, which occasionally manifest themselves as active galactic nuclei, more so at high redshifts than today. Well, there is an interesting approach to this. You can integrate quasar luminosity function as a function of time, now that we measured it, and add up all of the quasar light, by light I mean things from radio all the way through gamma rays, ever emitted. And then you can assume that there was certain efficiency of accretion. We remember that's estimated to be about 10%. So about 10% of all of the rest mass that was accreted into black holes was turned into the luminosity that we just added up. And the rest is now in form of the black hole masses. So that implies that today there is certain mean density of supermassive black holes, which is of the order of some hundreds of thousands of solar masses per cubic megaparsec. And when you compare that with number densities of galaxies, essentially it implies that on average, typical galaxy like L-star galaxy, a Milky Way type galaxy, would have about 10 million solar mass black hole in it. And Milky Way has 3 or 4 million solar mass black hole, Andromeda has a somewhat bigger one, and so on. So just from adding up the quasar light, we can say something about volume, density, or abundance of black holes today. And indeed, we find out from the correlation between masses of black holes and their host galaxies' luminosities or stellar masses that approximately 0.1% of the host galaxy's mass, or rather of the all-stellar component of the host galaxy mass, is turned into the black hole. And that turns out to match exactly, within the error bars, the argument from adding up the quasar light. So this is good. This is a completely independent argument, and we reach the same conclusion. So it's indicative that we actually got the story right. So supermassive black holes are ubiquitous. They occurred in essentially all massive galaxies, not so much in dwarfs. And they were just normal phase of galaxy evolution. Now remember, the way to fuel active nuclei is the same way as to how to trigger bursts of star formation, and that is through dissipative merging. Gas loses energy very effectively, sinks to the middle, where it can trigger star formation, or it can fuel supermassive black hole. So this physical process can account for simultaneous growth of both galaxies or their stellar components, as well as their supermassive black holes. And indeed, we can model the process now in computers, in hydro simulations. This is a montage of phases of a merger of two spiral galaxies, each of which has a black hole and so on. And the same process of hierarchical dissipative merging then creates both, or contributes to evolution of both galaxies and supermassive black holes. So that alone can drive some of the observed correlations, but there is another component to this, and this is so-called AGN feedback. Not only is the input important, but also the output. Active nuclei can easily ionize interstellar medium of their host galaxies. Now that can actually stop star formation. So energy input by active nuclei can regulate star formation in their hosts. And if there's a lot of it, it can cut it off. Also, there is a mechanical luminosity, as you recall. All these relativistic electrons streaming out through jets and so on. And that mechanical luminosity can match electromagnetic luminosity. So Over typical lifetime integrated episodes of active nucleus activity, you may release of the order of 10 to the 60th ergs in luminosity or mechanical energy. Recall also that a binding energy of an average galaxy is more of the order of 10 to the 59 ergs. So even if small percentage of the energy generated by active nucleus is coupled somehow to the material of the galaxy itself, it can make profound effect on galaxy structure and growth. And we now think that this is what's happening, so it's this feedback mechanism that sharpens up the correlations that are observed. These are snapshots from a simulation trying to reproduce growth of a really massive black hole that ignites as a quasar at around redshift of 6 or a little higher. And it is possible to pile up enough material quickly enough through dissipative merging to actually generate these objects at the time scales that correspond to when we observe them. They're rare. These are like the most massive objects in the universe at the time, but they can exist. And so what's emerging today is a picture of quasar galaxy or supermassive black hole galaxy co-evolution and co-formation. They're both assembled in a similar fashion through hierarchical growth. Quasars can exert feedback onto their host galaxies. The two processes are tightly coupled. So these extreme objects or events are really part and parcel of the overall evolution of galaxies. And the next time, we will talk about the origins of those first supermassive black holes.